Hi everybody, welcome from HVACR Design Engineering. I am Tuya Ao. Now I want to talk about air handling unit. Air handling unit, which usually have acronym of AHU, are found in medium to large commercial and industrial buildings. They are usually located in the basement, on the roof, or on the floor of the building. AHU will serve a specified area or zone within a building, such as east side or office area from floor 1 to floor 10, or perhaps a single purpose, such as just the building toilet. Therefore, it's very common to find multiple AHU around a building. Some buildings, particularly old high-rise buildings, will have just one large AHU, which is usually located on the roof. This will supply the entire building. They might not have a rotunda. Some older designs rely on the air just simply leaking out of the building, but the design is not so common anymore in new buildings because it's very inefficient. Now it's most common to have multiple smaller AHU supplying different zones to give better control and higher quality space conditioning. Buildings are now also much more airtight, so we need to have a rotunda to regulate the pressure inside the building. Air handling unit condition and distribute air within a building. They take fresh ambient air from outside and then clean this, heat it or cool it, maybe humidify or dehumidify it, and then they will pull it through center wall around to the designated area within the building. Both units will have an additional run to them. Pull this dirty used air out from the room back to the AHU, where the fan will discharge it back into the atmosphere. Some of this rotten air or used air might be recirculated back into the fresh air supply to save energy. Let's have a look at a simple typical AHU design. In this very basic model, we have two AHU housing for supply and rotten air. At the very front, on the inlet and outlet of each housing, we have a grate to prevent objects from entering into a mechanical component inside the AHU. Here a photo of an AHU intake that will suck in a whole bunch of traps if the grate wasn't there. So that's why it's important to have this installed. At the inlet of a fresh air housing and the discharge of the rotten air housing, we have sun damper. The damper are multiple sheet of metal which can rotate. They get close to prevent air from entering or exiting the AHU. They can open fully to fully allow air in or out, and they can also vary their position somewhere in between to restrict the amount of air which can enter or exit. I show you some example photo of damper in AHU. One on the left has the motorized controller which change the position of the damper. After the damper, we have some filter. Filter are trying to catch all the dirt and dust etc. from entering the AHU and also the building. If we don't have this filter, the dust is going to build up inside the ductwork and within the mechanical equipment. It's also going to enter the building and be breathed in by the occupant as well as make the bearing dirty. Across each of the feeder band, we have a pressure sensor. Pressure sensor will measure how dirty the feeder are, and when the engineer wants it time to replace the feeder. As the feeder pick up that, and the amount of air that can flow through then is restricted air. This causes a pressure drop. Typically, we have some panel feeder or pre-feeder to catch larger dust particles. Then, we have some bed feeder to catch the smaller dust particles. The next thing we will find are the cooling and heating coil. The cooling and heating coil are to cool or heat the air. The air temperature of the supply air is measured as it leaves the AHU. This needs to be at a design temperature to keep the people inside the building comfortable. This design temperature is called the subwire. If the air temperature is below this value, the heating coil will add heat to increase the air temperature and bring it up to subwire. If the air is too hot, then the cooling coil will remove heat to lower the air temperature and also reach the subwire. The coil are heat exchanger. Inside the coil is a hot or cold fluid, usually something like a heated or chilled water, refrigerant or steam. Next, we have a fan. Fan is going to pull air in from outside and then through the damper, the feeder, the coil, and then push this out through the ductwork and around the building. Centrifugal fans are very common in old and existing AHU, but easy electronically commuted fans are now being installed and also retrofit for increased energy efficiency. Across the fan, we also have a pressure sensor. This will sense if the fan is running. If it's running, then it will create a pressure difference, and we can use this to detect a failure in the equipment and warn the engineer of a problem. We also likely have a depth pressure sensor shortly after the fan discharge. This will read the static pressure, and in some AHU, the speed of the fan is controlled as a result of the pressure in the tank. This will also very often find a variable speed drive connected to the fan or variable volume system. Then we have a ductwork which sends the air around the building to the designated area. We also have rotating ductwork coming back, which is bringing all the used air from the building back to a separate part of the AHU. This rotating AHU is also located near the supply, but it doesn't have to be. It can be located as well in a building. The rotating AHU in its simpler form has just a fan and damper inside. The fan is pulling air in from around the building and then pushing it all the way out of the building into the atmosphere. The damper is located at the exit of the rotating AHU housing and will close when the AHU turns off. When you are at the cold part of the wall, where air temperature reach freezing point, then we'll find a preheater in the inlet of the fresh air intake. This is usually an electrical heater. For example, when the outside air gets around 6 degrees Celsius or 42.8 degrees Fahrenheit, the heater will turn on and heat up the air to protect the component inside from frost. Otherwise, this could be freeze the heating and cooling coil inside and burst them. Some buildings need to control the humidity of the air they supply into the building. We will find humidity sensor at the outlet of the supply AHU to measure the moisture in the air supply. This will also have a set point for how much moisture should be in the air by design. If the air moisture content is below this value, then we need to introduce moisture into the air using humidifier. Humidifier is one of the last things in AHU. Humidifier will usually either add strain or a spray of water mist into the air. Humidifiers are crucial for places like document store and computer room. If the air is too humid, then this can be reduced through the cooling coil. As the air hits the cooling coil, the cold surface will cause the moisture within the air to condense and flow away by fan. You will find a drain pan under the cooling coil to catch the water and drain this way. The cooling coil can be used to further reduce the moisture content by reducing more heat, but of course, this will decrease the air temperature below the supply set point. If this occurs, then the heating coil can be turned on to bring the temperature back up. This will work, although it is very energy intensive. If the supply and return AHU are located in different areas, then a common way to recover some of the thermal energy is to use a run-around coil. This uses a coil in both AHU and fan circulate water between the two. This will pick up waste heat from the return AHU and add this to the supply AHU. This will reduce the heating demand on the heating coil, and when the outside air temperature is below the supply air set point temperature and the return air temperature higher than the supply, the heat would otherwise be wasted as it is simply rejected to atmosphere. As the fan will consume electricity, it is only cost effective to turn on if the energy saved is more than the fan will consume. Another very common version we will come across is to have a deficit between the exhaust and the fresh air intake. This allows some of the exhaust air to be recirculated back into the fresh air intake to offset the heating and cooling demand. An additional damper sits within the connecting duct to control how much air can be recirculated. This is safe and healthy to do so, but you will need to ensure that the exhaust air has a lower CO2 count, so we need some CO2 sensor to monitor that. If the CO2 level is too high, then the air can be reused. The mixer damper will close and all the return air will be rejected from the building. When in recirculation mode, the main inlet and outlet damper will not fully close in this setup because we will still need the minimum amount of fresh air to enter the building. We can use this in the winter if the return air is warmer than the outside air, and we can also use this in the summer if the return air is cooler than the outside air respected to the supply set point temperature. We also need some temperature sensor at the intake return just after the mixing region. Some buildings require 100% fresh air, so this strategy can be used everywhere. Another variation we might come across is the air plate heat exchanger. This uses thin sheet of metal to separate the two streams of air so that they do not come into direct contact or mix at all. The temperature difference between the two air streams will cause the heat to transfer over from the hot exhaust stream through the metal wall of the heat exchanger and into the cold intake stream. The two air streams need to cross over for this to occur. Just remember, the airstream are not missing. Thank you very much for watching my video.